All right. So this video hopefully will be a lot shorter than the rest, but we'll see. I'm going to show the derivation of where the formula comes from for geometric series, the one that we did in class, and then I'm just gonna do a bunch of examples. Hopefully that will help clear some things up with geometric series for you guys, and yeah. So this video pretty much is gonna stay in 10.2. I'm gonna tell Gina to focus on 10.1, on some examples from 10.1 in class, and I guess whatever I don't get to in this video, she can do in recitation. All right, so here we go. The formula for, so just to recap, geometric series, I can spell geometric series. All right, what makes a geometric series a geometric series? It's a series, so you need the sum sign. That looks like this, where a is that starting value, and every subsequent term is going to have a will be multiplied by that factor, that the common ratio on each time, right? And so to show, and I think I said, so in class I said you need to show two things to say geometric series converges. First thing is that, well, you need to state the series is geometric. Is geometric, which means in class the way I did it was I identified the a term and then identified the r term, and if it has an a and an r being raised to, and the r is being raised to the n, you know it's a geometric series. So that's the first part is kind of easy. It's just, identify the a, identify the r, and it should be good to go. Second thing is that r, that common ratio, if it's less than 1, then the series converges to a over 1 minus r. All right, so in this part, we're going to show why is this the case? Why is the sum that? All right, so let's take some arbitrary geometric series. So that means, so given, right, some arbitrary geometric series. So it starts with a plus a r to the n. I'm sorry, not n. I'm sorry, to the first power, and then plus a r to the second power, plus dot 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 dot, and eventually, right, because these are infinite series, like it's gonna go off to infinity. But we're actually gonna like stop at a certain capital N value. I'm gonna explain this capital N in just a second. All right, but please note there is more after this, right? It'll keep going forever and ever and ever. But we're going to do something at the end of the proof, towards the end, to kind of do that for us. We're going to use like limits. So what this means is I'm stopping at some finite sum. And they have a special name for this. This is called the partial sum. Not so important. I mean, kind of is important, but don't worry about the vocab for now. So if I have some geometric series, I stop somewhere. And then all I'm gonna do is take this line right here, I'll label this line 1, and I'm gonna multiply it by r. Okay, I'm gonna multiply by r one more time. What would I get? Well, I'm just essentially multiplying each term by r. So it becomes ar plus ar squared plus ar cubed plus blah 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 plus ar to the n plus ar to the n plus 1, because I'm multiplying everything. Like this becomes that, right? The one before it becomes that, right? The 2 became the 3, this became that, and that became that, so on and so forth. If that makes sense, right? I'll line it up. Sorry, I'll line it up to make it look prettier. All right, so ar to the capital N plus 1, and then the one before that is ar to the capital N. Right, the dot 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 just means everything in between, right? Because we don't want to write everything in between. All right, here we go. Ready? We are going to perform some algebra here. We are going to subtract these two lines, right? We're going to subtract the first line from the second line from the first line, and something really interesting happens here. Let's look, right? This AR is going to kill that AR, right? Because like I said, I'm subtracting all of this. Right, so the AR is going to cancel out. The AR squared is going to cancel out with this AR squared. The one after that is going to cancel out with this one. This one's going to cancel out with this one. Right, so essentially all the middle terms Oh, wait, I went too much, sorry. All the terms essentially like kind of cancel out with each other, except for the a and the ar to the n plus 1, right? So what's left over? You're going to get a plus ar to the n plus 1. Make sense so far? Hope so. All right. We want to figure out, right, because once again, it's easy to kind of get lost in what we're trying to do. We're trying to figure out s sub n. We're trying to figure out the partial sum. Okay? So we got to do some factoring here, right? I'm going to factor out an s sub n. Left with 1 minus r is equal to a plus ar to the capital N plus 1. And we divide through by 1 minus r. Algebra, my dear Watson, right? Whoops. So that's it. What did we just figure out? We just figured out that the partial sum, when we stop at some n value, right, is equal to this ugly looking thing. But we don't want the partial sum. We want the actual sum. And also, like, a hint is like, wait, that doesn't look like this guy, right? It looks kind of like it, but it doesn't look exactly like it. So we need to consider a couple things here. The first thing we need to consider are our wow, that's really confusing to say. Are our R values. Whoops. You need to consider the R values here. What kind of R values make sense? If I let n go to infinity, if you think about it, right? Because that's what you want to do. You want the capital N to go to infinity of this thing. A plus a r to the capital N plus 1 all over 1 minus r. If I let n go to infinity, I would be getting the rest of the series. That's what I was saying in the beginning, right? Like, we stopped at n, but this thing has more terms after that, right? It goes on and on and on. Well, if I let that capital N now go to infinity, this is going to be like the true sum of that series, right? So that's the difference here. So in this case, right, if we let this n continue to grow to infinity, go forever and ever and ever, think about it. R is a constant. This is going to be our common ratio that exists, right? In our geometric series. If my common ratio was a number that's bigger than 1, think about it, right? Like 1.5 or 2 or 7 or whatever, right? If I plug that value in here, what's going to happen? Well, the exponent is going to be raised to infinity. Well, not infinity exactly, but it's going to go to infinity, and this whole thing is going to blow up. It's going to blow up to infinity. It's going to diverge. It's going to give us stuff that doesn't work. If you don't believe me? Try it. Let r equal, I don't know, 2. If that's the case, you get a plus, a times 2 to the n plus 1 all over negative 1. Limit as n goes to infinity, right? You guys can see it. This right here is like it's like a bomb. It's gonna go all the way up to infinity, and this whole thing will go to infinity. It'll diverge. And you notice that the only values that will make this work are in fact values, in between 1 and negative 1. Actually, no, 1 doesn't work, sorry. Right? Because think about it, if you add 1 up an infinite amount of times, that's just going to diverge, right? 1 plus 1 plus 1 plus 1 plus 1. An infinite amount of times, that's going to diverge too. So we can't even use 1. It needs to be, in other words, fractional values, right? Like 1/2 or 1/3 or 7/8 or any value that's in between 1 and negative 1. Any value that lives there, right? Watch. If in this case now, if I let r equal, I'm just going to do 1/2 now, and I do the same exact thing, I get a plus a times 1/2 now to the n plus 1 all over, what is that, 1? And if I let this now go to infinity, well, what happens when a fraction is being raised to a really, really big number? What do you guys think? It's going to go to 0, right? Meaning this whole thing goes to 0. That second term on the numerator, it just goes away. So when we are considering, so it's like when we are considering the values in between 1 and -1, this thing right here, this thing right here, the thing that we found earlier, right? This second term right here, this guy right here, it's kind of like we can kind of disregard it because we're letting n go to infinity, and essentially a plus ar to the n plus 1 all over 1 minus r. When we do this n going to infinity action, this becomes a over 1 minus r is the true sum. That's where it comes from. But this is only true. You can only do this if the common ratio is in between 1 and -1. I really hope that makes sense. And that's why the formula is the way it is. All right. On top of that, please make sure that you are also stating that the series is geometric, because obviously if it's not a geometric series, you can't use the geometric series formula. All right. Okay, so that's where the formula comes from. Let's do, how much time do I, oh, wow, 11 minutes, not bad. Let's do, I'll just call this example fun. Let's do another geometric series example, one that I couldn't get to in class. I don't know, let's see here. N equals 3 to infinity, 7 times -3/4 to the end. So, for this one, a couple things you got to watch out for, all right? Your A value can be misleading, all right? Some of you may look at this and be like, this is A, right? But that is wrong. You are wrong. This is not your A value. What is A defined as? If you don't remember, A is the first term in the series, right? So you got to watch out. This index could be the death of you if you do not pay attention to it. Because if you look, our first term is not n equals 0 when n equals 0. If it was, if n started at 0 for this one, then yes, 7 would be the A value, right? But it's not. So please, please, please pay attention to the index. Pay attention to the index. If you're not sure what it is, just plug it in, right? If I plug in n equals 3, I get 7 times -3 to the third over 4 to the fourth. And that is your A value. That's your first term. Your next one is going to be, what is this? 7 times -3 to the, oh, it's going to be positive because it's even, to the fourth. So 3 to the fourth over 4 to the fourth. Plus so on and so forth, right? However, I know you guys might be thinking, oh, so that means this isn't going to be the R value, right? That's not true. This is, in fact, the R value. Why? How is R defined? The ratio multiplied to each term. On every single term, you are multiplying -3/4 to each term. Do you guys see that, right? Only the 3/4 will be changing from term to term. So you got to watch out for that. I think the only thing to really watch out for is just the A value, the tricky A values. All right. So how do we do this? How do we show that this is convergent or divergent, and what does it converge to? All right. Let's see here. First thing you state is the series is geometric. Once again, you must say that the series is geometric. The A value is equal to 7 times -3. We'll figure that out in just a second. That's your A value. And the R value, sorry, not the absolute value R, but the R, just R, is equal to -3/4. Because that's what you're multiplying on every step. On every, on every term. Second thing, since absolute value of R, which is equal to 3/4 in this case, is less than 1, we can just go straight to the formula. We know the series converge to We just use the formula. Why? Because this is a converging series, and where the common ratio is less than 1, and it's geometric, right? So it's going to converge to S equals the first term, which is 7 times negative 3 over, I hope you guys figured, I don't want to do this, honestly. You guys can figure that out. Over 1 minus negative 3/4. I'm going to cheat. I'm looking at the book. This is example 4, by the way. This is on page 569. Should have said that first. Sorry. But yeah, I'm just going to look at the answer. You guys can do the algebra, but the answer should be negative 27 over 16. Pretty crazy, right? We have this infinite series going off to infinity, and we get a finite value. In this case, it ended up being negative. All right, so hopefully that was a clear example, right? Please make sure you're writing down your justifications. Please make sure you're identifying your first term properly, you know? And yeah, I'll do one more. You guys can stop watching here if you want, but I'll do one more just for funsies. Example super funsies. But this is technically example 5. It's also on page 569. Something cool you can do with geometric series is rewrite repeating decimals. You guys ever wonder how your calculators do this? They use geometric series. Don't believe me? Watch. So, if I have, let's say, 0.212121 ... You can rewrite this into improper fractions, right? You just need to express this as a geometric series. What? You can do that? Watch. Ready? This is the same thing as 21 over 100 plus 21 over... Oh, sorry. I believe it's 2 more zeros. So it's going to be 100 squared. And then 21 over 100 cubed. Yep. And then so on and so forth, right? It's like you're writing every 2 decimal places by raising 100 to the next power, if that makes sense, right? And this thing is going to go on forever and ever and ever and ever. Well, we can express this as a geometric series, believe it or not, right? This is going to be the same thing as, let's see, I want my first term to be 21 over 100, because that's A, right? This is A, times what's being multiplied on each step? It looks like 1 over 100. We're starting at 0, going to infinity. What did I do? I just rewrote my thing into series notation, right? So this is like this strung out version. But this is called series notation. When obviously when there's a summation, summation notation. That's what it's called. Summation notation. All right. Whichever like form you prefer, whatever you need to do to identify A and R. But we kind of identified it a lot, right? A is 21 over 100. R is 1 over 100. So this is geometric. And then the second part, since R, absolute value of R is less than 1, it's 1 over 100, the sum is going to converges to the sum, which is 21 over 100 over 1 minus 1 over 100, which is equal to 21 over 100 over 99 over 100, or 21 over 99. Don't believe me? Oh, this reduces down, if you want, to 7 over 33. I'm just looking at the book. Don't believe me? Punch it into your calculator. You will see 2, 1, 2, 1, 2, 1, 2, 1, repeating over and over and over and over again. I really like these examples. These are a lot of fun, right? So, if you want, you can try this one. Try rewriting 0.123, 123, 123, ... Try this on your own, if you have the time. All right, guys, that's it for this video. Please, if you have any questions, reach out. especially with this geometric series stuff. This is the thing that's going to set us up for the later crazy series stuff. It gets pretty serious. Series is. Never mind. All right. I'll see you guys on Wednesday. Please study for that midterm.